I wanted to have a different speaker tonight, but that somehow got messed up, so I have to jump in and do something. So I prepared here a little presentation about some of the CMake stuff that I got in touch with lately, some of the testing stuff that I got in touch with lately, and some of the utils that I got in touch with lately. And it's kind of subtitled like a chaotic ride through parts of the infrastructure, because it doesn't necessarily follow a clear storyline. So apologies for that. There will be an example like for some of the work that I did. That's more of a storyline, but before that, it's more of a collection of different things. And the different things is, so I'm going to talk about some of the CMake. So for example, the projects versus the runtimes, certain flags, the dependencies. I think I got rid of them. We'll see. So for the tests, I will mostly look a bit on how we use testing, like in the build pods and on the daily basis for some of the lit tests, some of the configurations. And then I'm going to cover a few of the utils that are in tree for specifically for like test generation and working with IR if you encounter a bug in LLVM, and how to, like, for example, use LLVM bisect to reduce the LLVM reduce. This is a typo. LLVM reduce to reduce the IR. But yeah, we'll see. So this is sort of the agenda. Okay, so let's start with CMake. So first off, there's a distinction in LLVM language between projects and runtimes. With the projects, they use what is called the host toolchain. So basically what you have in on your host installed as the compiler, or you give as the CMake CXX compiler. And it will typically just install into like your top level install directory that you give it. The runtimes, on the other hand, they use as the compiler typically your freshly built Clang from Intree, and the installation will go into like the top level and then lib and then some subdirectories potentially. So for the projects, this is how you would use that as a CMake flag. You would do -d and LLVM enable projects, and this is for like Clang, LLVM, and LLD as an example. But also, let's say MLIR is another project here. And as mentioned, so this will pick up your host toolchain. So if you have an ancient GCC, for example, the projects in here need to be buildable with that ancient GCC. And that's interesting, for example, if you want to support let's say SUSE Linux 15, which has like GCC 7.5 as the host compiler, and some of the MLIR tests, for example, that we just recently fixed them because they were relying on something that that GCC version doesn't provide. Yeah, so that's something that if you put it in enable projects, your host compiler has to have the ability to build these things. Then something that is called LLVM Ccache build, and you will see that flag used in some of the buildbot configs that have been around for quite some time. That is now kind of considered the legacy option because CMake introduced something that is called CMake C or CMake CXX compiler launcher, where you can give it the Ccache. But in case you, again, if you're running on an older host that doesn't have a more modern CMake version installed, you can use that option to kind of work around that limitation of the missing CMake CXX compiler launcher flag. And you will see this also in some of the buildbot configs that run on older OSs that do not have a more modern CMake installed. And then we do have what is called LLVM use linker. And so this is the linker that is to be used while you're building LLVM, right? So for example, if you want to speed up your build and not rely on LD, you can, for example, use gold here, or potentially nowadays you would potentially want to use mold. Though, for example, we typically don't do that. We just rely on LD, but that's for funny reasons, for like infrastructure managing stuff. But yeah, so this is how you would choose the linker that gets picked up during the build of LLVM. And then there's also this thing called Clang default linker, and that is where you select which linker the build Clang will typically use for linking. So there's difference here. So potentially you cannot use gold or LLD with this option because you don't have it installed in the system, but you can use it here because it was enabled in the projects. And then this option will just pick up the freshly built LLD from your build tree. Yes. Yes. Okay, so the question is, if we enable a runtime and we then specify some linker here and some linker here, which one will be picked up? I believe it's this one. Because this one is then, because you use the freshly built Clang, you're gonna use whatever that thing will invoke in the linking stage. And so, for example, on our toolchain, we rely on this, where we specify LLD that's not installed on the host, so we'll pick it up from the build tree for all our testing and building. Then something that I only encountered when I actually got the build bots, inherited the build bots sort of, is that you can pass lit arguments already during CMake time. So they will be automatically passed on to whenever you run lit tests. So for example, if you do like a ninja check LLVM and you give it that particular lit argument, every single test will run with a timeout of 2 minutes. And as a little like side note, this will require some Python package be installed. It's called psutil. That's not the default package, so you have to install that Python package when you're setting up a machine to be able to use that. And then this is LLVM enable runtime. So here we have, for example, compiler RT, OpenMP, and the now new fresh offload runtime. So this is what you would do now if you want to enable OpenMP with GPU offloading. You would typically build compiler RT, OpenMP, and offload as a runtime. And this will, as mentioned, pick up the news Clang, which in this case is particularly relevant because for the GPU device runtime library that we built for the specific GPU architecture, we actually rely on modern Clang features. So we want to be in sync with the most up-to-date Clang here. And then that's an option that I just learned about like 2 weeks ago. That's LLVM enable per runtime, LLVM enable per target runtime dir. And that is if you enable a runtime, if you set this to true, and I believe that's now the default, it will be placing every runtime library into lib and then slash and then the host identifier like x86, 64, Linux or something. Whereas if you would set this to false, it would just put everything into /lib, more or less. So this gives you the ability to have this per target. So if you're building, for example, for cross compilation, or for different targets, you probably want to set this to true. And then this is something that came up in a project that is called libc for GPU. If you've not heard of that project, it's pretty cool. Basically, LLVM has this libc project, which is more or less a re-implementation of libc. And the idea is that you kind of provide every function that libc has also on the GPU. So that you can, in your regular or in your GPU kernel code, you can just say malloc blah 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 and then printf, and the magic happens behind the scenes to just do whatever is needed to give you some memory on the GPU, either from the host or from a GPU allocator, or printf, like send some bytes back to the host, do some syscall and whatever. And for that, we now use a more or less like a cross compilation infrastructure, so that the GPU is just observed as a new or as another cross compilation architecture or target. And this is where that thing comes from. So here, for example, you would enable the default target, which is just for your host, but also like the AMD GCN, AMD HSA target triplet, which will build libc in kind of cross compilation mode for an AMD GPU. And then let's see if my memory serves me right. And then there's this even more obscure option where you have runtimes underbar, then the target, and then underbar LLVM enable runtimes. And this is for a given target that you mentioned here. You can specify this thing and which runtimes you actually want to enable in that cross compilation scheme. Yes, it's completely messed up, and there's actually now an option that is just dash D, I think it's LLVM enable GPU libc or something, that will just do all of this for you. Um, but yeah, so this is kind of the weirdnesses that we have to like go through the motions if we want to build libc for GPU as of now. But it will be better soon. Now, it's just some final comments about the whole enable runtimes, enable projects thing. In general, that's pretty convenient because you don't have to like manually do staged builds of your infrastructure anymore, where you would manually build LLVM clang LLD and then have another manual CMake invocation pointing to the just built clangs and LLDs and whatever to just to compile a runtime, right? That will just, if you enable Clang LLVM LLD in projects and then enable compiler RT, OpenMP and offload in runtimes, it will just work automatically everything, and you just type a single like ninja to build all of this. One of the kind of the parts that are not so cool is that you cannot distinguish for runtimes and projects with the CMake build type. So if you just say CMake build type release, this will build also your Clang and LLVM and LLD in debug mode, which can make the second step quite time consuming because a debug LLVM is not necessarily the fastest way of using it. So that's kind of a downside. And then there's some, and I have to admit that I don't understand everything of this. There's some flags that are propagated to both builds in some obscure way, others don't. And we actually hunted down a bug or a build-bot breakage that just came from two different CMake configurations that the committer was using and I was using on the build-bot. Because, as mentioned, this propagated some compile flag into the actual like compilation of the of a runtime, which was supposed to just happen in the projects. So that was kind of weird. But yeah, there's 100,000 probably CMake variables more that like you can use to tweak things. Um, and there's not a lot of good documentation out there. That's unfortunate, but that's the way it is. Okay, so here that's just a quick example, and I don't know if you can actually read this. The only thing that I did here is I just played around with some of the flags and basically how we do that in the on the build bots sometimes. So this is, I just do a CMake with nothing spectacular. So Clang LLVM LLD. I only enable the compiler RT runtime here. I use Clang default linker is LLD and I build release mode. And this is basically, so we configure about 18 seconds and then we build with 28 threads on a desktop machine for like 15 minutes. If we're just using regular makefiles or the Unix makefiles generator. If we now switch to Ninja, we configure a little shorter, so 12 seconds here, and we bring the compilation time down to about 14 minutes. Now I use the legacy Ccache build option on, so configure time doesn't change, compile time doesn't change. But the next thing that I did was then I did a git pull, and I'm sorry, this is smaller now. And for some weird reason, I had about a delta of about 16,000 commits, so I probably didn't like update my repository for quite some time. And that pretty much is just a full rebuild, because you cannot like benefit from anything you cached. So the compilation time again was about 16.5 minutes here. If we then just like do a reconfigure with the same options, with the additional OpenMP runtime here, and then build this, it will actually only build OpenMP because everything else is still in Ccache, and we are getting the whole compilation for about 7.5 seconds, which is quite nice because you don't have to rebuild everything again, right? And then I just removed everything in the build directory and did a reconfigure with the exact same CMake invocation, and now did another Ninja build, which in theory would rebuild the whole thing. But since Ccache is still hot, we actually can compile it in only a minute and 16 seconds. So if you're doing like regular rebuilds with only small deltas, using Ccache is really, I think, the way to go. And this is actually what pretty much all of the build bots do, because otherwise we wouldn't like be able to keep up with the commit frequency that we see upstream. So we have about a turnaround time in most of the build bots from 3 to 5 minutes per build, and that's what we also aim for. Yeah, without CMake, we couldn't do that. Okay, now we move on to tests. First of all, lit filter. This is probably the lit option that I use the most, because it lets you reduce the number of tests that are actually run by only running the tests that actually match this pattern. So if you have, let's say, a lot of offloading tests, and some of them are actually in a folder called API, then this invocation will only run those tests, right? So it will skip all the other ones. So that's quite handy, and you can actually also give it like a specific name of a single lit test, and it will only run this one. So that's quite nice if you want to like try something, or if you have a flaky test, which of course OpenMP upstream doesn't have any of the flaky tests. That's how you typically do that. The other one is time tests. And if you've never used that, that's quite helpful if you have like weird testing behavior and think you're spending too much time, because that actually captures and prints the individual test runtimes, but also gives you a histogram of things. So if you do that, we will see, so this is a screenshot from one of our build bots. The slowest tests are then here listed. So we see the slowest one is a JIT test that we have that takes about 14 seconds. Then we have one that takes about 11, and then you see that going down to like some of the other seconds here. And also it will print you this kind of histogram on the command line where we will see like the interval here that these tests take to run. And then you also get the count of how many actually fall into that interval. And so we see that we're okay. We're doing okay here, right? We're mostly down to like a couple of seconds for our tests upstream. That's okay. We may want to do something about those. And then this is something that's that we introduced in all of our build bots because of an issue we were seeing that well, nobody's really sure where that comes from. But we introduce or we enforce a timeout per test case of 2 minutes. And that will actually, in build bots, that will actually be propagated into the overview that the test didn't fail or wasn't like the whole thing wasn't killed, but the test itself ran into a timeout. So you can actually like look at which test cases typically run into this timeout to do some sort of like bisection or just like keep a list of things to look into. So that was quite handy, and you don't run a risk of your like CI or testing just getting completely out of hand and running for forever until something just kills it. Okay, that brings us to the utils section. For the utils, just as a disclaimer, this only covers a very small subset, and some of the things I have not used but only like seen and think they are very useful or could be very useful. So keep that in mind if you want to ask questions or something. The answer I can potentially just give you for some of those things is I don't know. Okay. First of all is LLVM reduce. So this is used to reduce a input bitcode or LL file to a minimum that kind of still reproduces the error, and you can use it pretty much like shown here. So you call it, you give it a test script, and I'll have an example that shows how I think even on some other slide how that should look like, and then the input file. Obviously, there's the reference to the command line documentation. And that just runs tests to see if the error still happens, and like throws away IR, which is typically the case because you don't need like hundreds and thousands of lines of IR to just like hit a specific assertion or something. Then there's this kind of handy thing which is called update test checks.py, and it's a Python script that will just generate the typical lit check lines that you have and see in tests for you. So if you know your thing generates the right answer, you have your run lines in the test case, and you give it a option here, and we will see an example for that. And then it will just generate check lines for you and introduce them into the file. So you don't have to write all these things manually, which for some of the in-tree test cases, that would be, well, probably like a week's worth of time of work or something. Okay, so here, this is actually something from the example that I'm going to walk you through at the end of this presentation. And we see here at the top it says, note assertions have been auto-generated by util/update analyze testchecks.py with the filter argument LV : found estimated cost of something for VF, something for instruction, blah, blah, blah. And then I had this run line here, which has the up-passes loop vectorize in here, debug only loop vectorize, blah, blah. And those check lines were just auto-generated for me. So I did not write any of these myself. And what that actually tests and why that's there, we're going to walk through the example at the end of this talk. Then there's this thing, update test body.py. And I have not used this before. It's for, according to the PR here, it's for help in creating clean assembly test files. So you can put high-level source code as comments into your assembly test files, and this script will like generate parts of the assembly from these comments and get rid of some of the parts, so that you don't have to like overly complicate the actual test case file. That's interesting, and I think this has plenty of examples here in the PR for like how this works. So if you're curious about that, please go look there, because as mentioned, I have no idea how this works and I have not used it before. Just wanted to point it out. And then there's also update CC test checks, which is Clang CodeGen things. So it's the same, it just updates test files. So there's different update something test checks that you can use, and there's even like an any test checks top level kind of script that will dispatch to the different specific ones depending on your actual test case. I didn't get this to work though, so I'm not sure. But yeah, so this is used in quite many of the OpenMP CodeGen tests. Then obviously Git Clang format, in case you didn't know so far or have not used it. That's quite a handy tool because it will only Git Clang format the actual diff that you have in a Git commit. So for example, if you worked on something, you Git committed it, and you have like the commit sitting on as head, you can use this thing to just Git Clang format the diff between your current patch and the patch before that. So it won't like reformat the whole file. That's handy if a lot of parts of the file are not necessarily formatted correctly, and you don't want to introduce a lot of noise in a PR or a patch, then this will just format the diff for you. So that's good to use. It's yes, exactly. Yeah, exactly. Exactly. It does not format the whole file. It will only format the diff, and that's quite handy. Specifically, if you want to like slowly introduce a new format, or have changed things, or don't want to do like everybody stops working. We're gonna format the whole tree. Commit it. Things have been done in the past. I think LLVM went through a couple of these. At least they went through one. But yeah, so this will only like format the div. Okay. Yeah, exactly. Okay, so now I didn't know how to title this section, but this is actually how are some of these tools at least used. Um, and this is basically inspired by me like starting my work on Monday. And I was out for a wedding party over the weekend, and I came back to work on Monday. And I was like, okay, let's like look through our nightlies, emails, whatever, what you do on Monday mornings, and there's this. So everything's red, everything is like broken. I was like, shit. This wasn't. This was all green on Friday. Okay, so something happened. Um, And it was pretty much only that specific mini application. So mini QMC is like a mini quantum Monte Carlo particle simulator, whatever. Okay, so now let's dig into this a little bit. How do we? Okay, so how do we do that? So we kind of first identify suspects via some sort of like bisecting. In our case, it's typically from upstream merges. Um, Or if you're just working upstream, you probably just have your commit history and go through that. But typically, it's not like everything is a suspect, but only specific ones. Then you kind of compare the last known good configuration with the offending configurations. This is probably specific to that we have these like merge points. And typically, we just start with these merge points to see which merge broke our build, basically. And then first we report the problem upstream, right? That's of course the first thing to do. If you know which part broke it, you report it. And then also you kind of work on a reproducer to help in debugging the issue or in fixing it. And that just depends on the severity or the complexity of the problem. Um, yeah, minimum reproducer and patch. Okay, so this is what actually came when I tried to build that application manually. So we get a stack trace. There's an assertion error happening here in, what is that, x86 TTI impl get interleave memory up cost AVX512. And it's an unknown type. So I was like, okay, great. I have no idea where this is, what this is, and why it happens. Okay, let's start. So I went through the commit history and again, we have these merge points. So I started with these merge points and then looked like which commits came in to these merges. And then I simply did, this could be it. So I git reverted that commit and I tested if the application built again. And once I found the offending commit, I knew at least what it was. Okay. Of course, if that revert didn't work, you kind of revert the revert or just like reset back to wherever you started and do the next suspect. So I found out this code gen. Forbid passing a pointer type to MVT, get VT, and EVT, get VT, get EVT. Okay, whatever. I don't know. So first I reported in this issue that this broke something. And I got the backtrace, and then I thought like, okay, so I have to fix the issue because it also impacted one of the customer applications potentially, for which MiniQMC is kind of a proxy. And we didn't want to just revert downstream because that typically just asks for more chaos further down the road. Okay. So I read also the PR comments and everything, and then basically I just implemented a workaround that solved the issue for as much as I could tell at that point. So I tested it locally if it fixes the issue. I tested locally if all the LLVM tests still work, right? Because you don't want to break other stuff. So, and then I opened a PR upstream and waited for feedback. And I got feedback, and this is needs test. I was like, shit. And this is kind of a colleague of mine, so he's working at AMD, right? So okay, cool. I was like, shit, I got to do something here. Now, how do we get the test? Okay, so I again like got back to the application that crashed, or that didn't build. Sorry, where the assertion triggered. And then I looked at the like what Clang says for like bug reports, and it says you should like upload the preprocessed C++ source and like the build script and whatever. So I looked, this was about 12 megabytes of C++ with about 310,000 lines of code, and that's not helpful as a test. At least I wouldn't think that that's helpful. Okay. So then I kind of looked around, what can I do? And basically LLVM reduce was what I wanted to use. But how do I get the IR? Because that didn't produce any IR. So it's an OpenMP offloading program. So there's the save temps command line option that kind of outputs temporary files all over the place. And in that particular instance, actually outputted what I wanted. So that's great. So I used that. So there was a dumped IR file that's about 17 megabytes with around 270,000 lines of IR. Okay, that's not helpful either as a test, but it's a starting point to LLVM reduce, right? So LLVM reduce to the rescue. Okay, so LLVM reduce takes as argument a shell script that would like do the build or apply whatever you tell it to do with the IR file. And typically it looks like this. So you kind of $1 obviously is your IR file, and then you do like opt. In my case, I had to pass in O3, and then I grabbed for unknown type. That was basically, do I trigger that assertion? Yes. So the question is whether I need to do that, if there's otherwise a different error thrown, whether it's considered broken. The honest answer is I don't know. Like all the examples tell it to like do this so that you find your error. Everybody gets one, I guess, but you want to find your error, right? But yeah, so I did this, and then I spent some time to find out that first of all, it needs +x, so it needs to be marked executable. Otherwise, you will get a POSIX spawn something weird error. And then it still didn't work, so more Stack Overflow. And I found that it needs the shebang. If you don't give it a shebang, it will again tell you it's a POSIX spawn error. It won't work. It won't run. It won't do anything. So you have to have a shebang in here, and you have to give it set the +x executable flag. Otherwise, you're out of luck. But once you have all of these things, then I could just do LLVM reduce test find error sh, so this script with the large input.bc. And it took about a couple of minutes, maybe, like 2 or 3 maximum, on a beefy machine. Have to admit that, beefy machine. And it came with reduced file that had about 2.3 kilobytes and 54 lines of IR. So that's kind of workable. That still reproduced the issue. And it's actually suited for manual inspection. So from multiple hundred thousands of line down to this. But this doesn't have any check in here right now, right? This is just an IR file that triggers the assertion. Okay, so what next? The issue only occurred with -03. Okay, so that's no good. I mean, there's like a whole zoo of passes that run there, right? What would trigger that? Well, I mean, the assertion crashed in the loop vectorizer, so there's some idea of where it comes from. But let's just say, okay, we can just print the pipeline passes that are actually run, right? Yeah, okay, that's not so helpful because this is actually the number of passes that are run, or all the passes. And this is, sorry, that should be higher up, but anyway. So this is, yeah. Okay, but the one thing that it does help you with is you know how these passes are called, right? Because before that, that was kind of opaque sometimes. So then what you can do is the assertion is in the loop vectorizer, and we kind of from this printout, we know that it's called loop vectorize. So what I then did was I print module scope and print before loop vectorize and --03. So this is basically telling up to run the O3 pipeline and give me the whole IR file or the whole IR that will be put into the loop vectorizer before the loop vectorizer. Okay, so that gives you exactly the IR that the loop vectorizer will crash on. And that output is actually 71 lines of code and serves as a reproducer because it triggers the issue. Okay, that's great. And this is then, I looked at the 74 lines to see what's actually in there, and I was able to throw away more stuff. So then I actually got down to 31 lines, and this is here. So this is the actual test case that triggers the issue still. And I honestly don't know what happens in here, but I also don't care too much because it triggers the issue. So we do have quite a few of like annotate or metadata. How are these called? Things called attributes. I think these are attributes here. We do have some metadata here with more attributes. One of the important things to note is that here we have the target CPU is ZenV4, which is kind of Zen version 4, I think. And we remember there was the assert came in like TTI x86, TTI Impel, blah, 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 cost AVX 512, right? So that thing potentially is important. Okay, so now that we have this, I added it to the open PR to the open PR that I did where our Matt commented like needs test, and then I received some more feedback that I could strip out some of the comments here and stuff. So I did that, and it made this even more like readable, down to 26 lines now. And as you can see, I got rid of most of the attributes and comments, and I only left in the attributes and version 4 here. I think that could also go away, but anyway. Yeah. Okay, but this still doesn't like check anything, right? That still just would trigger the assert. Okay. Did I not include this? Okay, let's see. So anyway, I added some checks. Maybe they're somewhere later in this talk. I don't know. I uploaded the this file with the automatically added check lines that I put in there. I obviously like manually validated before I did that the vectorized code that was there before the breakage was the same as with my fix and the patch and all of this, so that the cost model kind of did the same thing, the vectorizer kind of did the same thing. They were identical, so I was kind of confident enough to say like this fixes the issue and this is the test to like not have it break again. So I uploaded this and I received a thanks and it got approved. So that's great. So you see 17 hours ago. So this was approved last night. Slides were done after lunch. And then also Matt approved these changes like 3 hours ago. I was like, yeah, okay, I can commit them. That's perfect. And the actual change that I did in the PR that fixed the issue was kind of small. So instead that we get from the vector type, we get the scalar type, we now get the simple value type of the scalar type, but we also give it the data layout. Because apparently that's kind of the bug where in the code gen, it was mentioned that for the specific thing that was fixed or whatever, there should always be a data layout attached to that because it was about pointer types, and pointer types are different depending on the architecture. So they are different depending on the data layout. And so this is why you should query the what's that, target layout interface or something? Target layout information for the simple value type with a data layout for that particular scalar type. And so that was the fix. And I had this Monday morning probably, but all the rest was down to like coming up with a test case that actually kind of reproduced and showed the error. Yes, please. I don't know. What? So the question was what this line returned, and the answer is I don't know. Yeah. So I think this is like a something value type or vector type. I'm not sure. I actually looked it up on Monday, but I forgot until now. Um, and so you would kind of get the vector value type, and that would then depend on the target layout. But yeah, so that was the actual change, and this could be my last slide. No, I have the link to the PR if you just want to see like the whole carnage and the different incarnations of the thing. So yeah, if you're curious, um, check that out. And I think this is my last slide. Yes. So
Do you also have the changed the original post of the issue?
you mean the
You found the comment which was introduced in the bar.
yeah.
So do you have a comparison between
Yes, it's linked in the PR. Yeah. Okay, sorry, there was another question. Well, let's say we try to. I can the slides I can give you for sure. With the recording, we kind of have like the whole last year of recording still stuck around in some cloud hosting, but we'll see. Yeah, yeah, sure. Yeah, I can give you the slides. There's no worries. Yes. Okay.
So maybe it's not a direct question for you, but if you put IR test cases to the main project, whatever, how's the life cycle of such a test? Because if the IR changes, you have to adapt the IR that's written
Yeah.
in.
Yeah. So the question is about the like life cycle of the IR files if you put them in tree, and I think this is why these scripts exist. To be quite honest, but that's my personal take on it. I maybe Lucas knows more. Yeah. 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 So yeah. So these that's actually the point why I'm mentioning these update test checks is actually we did have we did have a change that would require you to touch like 1,000 LL files for some offset, for example. Um, and without these scripts, there's no way you could do that. Um, so this is and I only learned about these scripts when I started like working on these things with my day job. And, yeah, so that's why I thought I'd just share them here and share some of the pain I had to go through. Yes. Very good question. Yeah, so very good question. The question is about compiler RT, and it was typically add to projects. Should it be added to runtimes? Is there a difference? So there's a whole zoo of different answers to that question. Compiler RT, first of all, is special. That's kind of is the thing. So for as far as I know, and you may know more about that, I don't know how much. But anyway, so compiler RT is special in that case that Clang needs compiler RT, so it should be built kind of before Clang or in sync with Clang, at least in my understanding. And so if you put it in runtimes, you would first build Clang and then build compiler RT, which is not necessarily right. So they did some CMake trickery actually to build. I think they built parts of compiler RT before, then build Clang, and then build compiler RT as a whole with Clang or something. You kind of look weird, but I think so. Compiler RT is really a weird case because it provides these compile intrinsics. Best practice and what is I think currently suggested in discourse and Discord is that you put it into runtimes because it is a runtimes, and the CMake magic will take care of the rest. But yeah, that's Lucas. Whether you'd actually need to put LLVM in enabled projects, no. It should be enabled by default. Yeah.
After Clang. So you use the GCC tool chain to build Clang, and then use that Clang to build a compiler.
Exactly. This is what happens if you put it in runtimes, but I think there are like very tiny parts that Clang requires before. And so you would just like kind of bootstrap these parts to have Clang be buildable and then build the whole thing. But this is again, this is what I understood from different discussions, that there's a whole compiler to a special thing. Um, so that's kind of why I'm like, I'm not completely sure. For every other runtime, yes, you first build Clang with the host tool chain, and then build the runtimes. But compiler T is kind of special. Yeah. Okay. More questions? Yes. Oh yeah. Very good point. Yes. Very good point. Yeah. So the comment was that the next trick to make your builds faster is only enable the targets you actually care about. Right. Right. Okay. Everything is table gen. Yeah. Yeah. So the comment was, if you really want to do a debug build, you should enable table gen to be build optimized. So that helps a lot, especially with MLIR. Yes. Yeah. If you only care about debug info, you should do rel with deb info with this weirdly named CMake target that I always forget how to spell it actually. Okay. Other questions or comments? Yes, Lucas. Yep. Yeah. So the comment was about, yeah, enable shared libs for often rebuilds. We used to do that sometimes, but we kind of went away and just used Ccache. I think some of our developers still do that, or do both basically. So only build shared and do Ccache. But since no wait, I think the product also moved away from building shared libs. I'm not building static libs. I'm not sure. I would need to look that up. So maybe we're actually doing shared builds now. Yeah, good comment. Other questions or comments? Yes. So the question was, why did I do all the work and not the person who caused the issue? Well, because from all the infrastructure that LLVM has, there was no breakage. Only so we saw the breakage downstream in one of the projects that we care about. So this is why I wanted to fix it, or why I did not want to wait for the other person to care enough about this to fix it. Also, the test or the assert easily reproduced with the OpenMP offload build of MiniQMC. It did not easily reproduce with a non-GPU build of that thing. I don't know why, but that was the case. So it was for me just the easiest to just run the build script that we have, because we have scripted builds for all of this, get to the point where I know where it's failing, and then work from there. And then kind of I learned a lot along the way for like how would I do that, and how would I also like contribute these things then upstream. Yes. So the question is whether we came up with tests which would prevent that. Well, I mean, first of all, I would hope this one that I added would prevent some of the breakages. In general, I guess the answer is no, because you don't know. Um, and so the funny part about this potentially is that the initial PR that introduced that error actually noted that they looked through the code base of uses of that thing that they changed, and they didn't find any. So they actually they were aware, and they actually mentioned this change, they mentioned it in the PR, that if you really care about, this is what you should do. So it was more like, we hit this error and we know what to do. So this is why I came up with this PR so fast, right? Because I read their comments and I was able to do that. But then actually like getting to the example and getting to the test that would actually like make it, this is how it should be. That was kind of the hard part. That took a lot of time. Partly just due to my incompetence, probably. So for like, remember this thing? Yeah, that took me too long. So that's about 2 hours. Well, maybe not. 90 minutes. Yes.
You encounter this error in your downstream project.
Yes.
So this is code that is not in the LLVM repository.
No. So the question, or
Could not have seen or
okay, yeah,
else, but
yeah,
not
okay,
immediately see
yeah,
your code that or your test that
yeah,
triggered the
yeah, yeah. So the comment was that we saw this in downstream with code that is not upstream, and the comment is that's not completely true, but I have to rephrase what I said. So we saw this in a test that we do downstream. But once we saw that issue downstream, we were able to, if we just like swapped out our downstream clang for the upstream clang, we had the very same issue. So it was not due to downstream changes or downstream additions or whatever, but just due to something from upstream. Now about that they couldn't see it, it's just there's like a whole, any code could break with something you do, and there's only so much you can test, right? And so, for example, from our build bots that do like the post commit testing, so the configurations that we run, we see about 4 commits per hour in a normal day. That may increase to up to like 10 commits per hour or even more. So if it gets closer to the branching date of LLVM, that's probably where LLVM is kind of the most unstable it could ever be right before branching, because people try to rush in stuff, right? And so typically our build bots would want to build a single commit so that you get feedback to just the single to developer for that single patch that would like broke the build. But in the when we move closer, very close to branch date, we actually see that we have to that's called then batch up to like 5 or 10 commits because of the frequency. So even when something breaks the bot, you cannot pinpoint it to one commit. So this is where then you as a build bot maintainer have to manually, like locally, revert different things to see what actually breaks the build and comment on the PR and stuff. So that's kind of the thing. But yeah, so in general, the build bots give you like some layer of protection, but they won't catch everything. Even more so if you try to run longer tests or more builds of like actual applications, then you will kind of run into the problem that it just takes so long that you will always batch like, I don't know, 25 commits, 30 commits, 40 commits. And then it's it's up to you to decide how, how much am I willing to potentially spend on triaging this list of commits with like other build breakages and everything to figure out what actually broke that particular bot, right? And then we get to like, can you build pipelines where if this thing is broken, you don't run that thing and blah blah blah. But that's like a whole different talk, a whole different topic. Not just talk, but topic. Yeah. Okay, and I think pizza is here, so we continue discussions while having pizza and drinks. Thank you all, and take care.